Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I want to thank everybody for coming this morning. It's a little bit short notice, but we really appreciate you being here. I'm really excited to introduce Megan Watsky, who's with the Chandra X-ray Observatory. She's a communications officer for them. And she's going to talk about some of the books that she's been working on. The most recent one, we have copies of them up here. It's called Light, and that's actually in Costco. Shows you how many copies are out there. And then another really excellent one I'll open up is called Color the Universe, about the work at the Chandra X-ray Observatory and the whole idea around the work that they do around pulse color, et cetera. And there's another one, which is an earlier book called Your Ticket to the Universe. It's floating around. You guys can look at that. And so I'd like just to, let's all give Megan a warm welcome and take it away, Megan.
Thank you, Curtis, and thanks for all of you guys for taking some time out of your busy day to come and listen to what I have to say. As Curtis mentioned, I work for NASA's Chandra X-ray Observatory, and I don't know if you guys know about it or not, but most people have heard of Hubble, and that is obviously an orbiting telescope that looks at visible light. Chandra is a sister mission to Hubble, and instead it looks at X-ray light from space. It was launched in 1999 aboard the Space Shuttle Columbia, and it has been operating for 16 years. And so what I do in my day job is I am the press officer, which means that I translate the results from the telescope that scientists have, the discoveries, and turn them into press releases, press briefings, web stories, whatever. And a big part of telling the story of what has been discovered involves images. And that leads you down a bit of a path in and of itself. So most people, when they see something, say from Hubble, they'll say, oh, okay, if I had a big enough telescope, I would see that with my eyes, which is actually not really true, but we'll get to that. But if you start talking about X-rays, people start saying, well, why do you have a telescope that looks at X-rays? And so you inevitably have to talk about there are different kinds of light. And you go through the electromagnetic spectrum and all this. And so you have to start at the beginning, which is that there is more than the light that we can see with our eyes. We take this for granted if you're in a technical field or involved with physics in any way, but most people don't know that. They just think of light as being illumination. So that was sort of one of the reasons that I ended up doing, my co-author Kim Arcand and I ended up doing the light book, which is somewhere in the room, to basically just expose people to the different kinds of light that are out there, yeah, that one, and how, even if you don't know it, you use different kinds of light every day, and they affect us in different ways. The book I'm going to really focus on today, however, that's the white book there, is Coloring the Universe. And the story behind that book is our good friend Travis Rector is an astronomer up in the University of Alaska, and until recently I think he was the only astronomer in the whole state of Alaska. I think he now has a friend or a graduate student. And he has done a lot of work over the years taking images from places like Kitt Peak and Gemini and other mainly ground-based telescopes and turning them into pretty pictures. And that is something that some astronomers don't do. They just get their data, they analyze it, and they go on their merry way. Travis, over the years, has found, I think, both joy and personal satisfaction and purpose in turning the data that he takes and turning them into beautiful images that the public can understand and use. And you see these images everywhere. You see them on posters, you see them on billboards, you see them probably on, I don't know if I should say this, on the back of Apples, the screensavers, whatever. I mean, space images are very, very popular. And that, their popularity, I think, is a testament to the fact that people are interested in space. But there's a downside is in our digital world. And that means that people often question, is what they're seeing real? I mean, we live in, Star Wars will come out next week in case you haven't heard. There's a lot of digital effects out there. There's a lot of so there's a lot of digital effects out there in everything from movies to whatever, and there's a lot of photoshopping. And we now live in an age where to Photoshop is a verb and it's often a negative one, right? So People, have approached Travis and have approached Kim and myself over the years and said, that's really pretty, but you know what? You just made it up. Or is that really how it looks, or whatever? So the Coloring the Universe book is really aimed at explaining exactly how astronomers get these pictures, where the colors come from, and also, all the steps that we take to get there. So I will give you a little bit of an overview about what's in the book, and then give you some resources at the end if you want to hear more. So just to go back to the electromagnetic spectrum, so Chandra is the one, obviously, in the bottom. It looks at X-rays. If you look at the bottom, you'll sort of a little bit backwards. The left hand is gamma rays. The right hand is radio waves. And you can see that astronomers have an amazing toolkit at their disposal these days that basically, and this is just a sample, they have telescopes that look at almost every single part of the electromagnetic spectrum. And they really need this, not just for fun, they need this to fit in all the pieces of the puzzle that they have in order to get the complete picture of the universe. The nice corollary to that is that while they're answering these scientific questions, you often can get great data to make spectacular images. And these multi-wavelength images, I would argue, are some of the most profound ones we have out there. In fact, sometimes it looks almost, the single wavelength images almost look, to me, kind of naked. So I'll show you some examples in just a minute. But we use this analogy for the public that, if you just had your visible light, if you just had the light that we could see with our eyes, and you had to go, so say you have an alien friend that comes to the United States, and I'm from Boston, so you take him to Fenway, but the alien can only see down the third base line. So that's your vision if you just had visible light. So you're trying to explain the game to your alien friend. He's got to figure out the rules, like the score, all that stuff. It's next to impossible. That would be, even if you had Hubble, you would only be seeing down the third base line if you just looked at the universe in visible light. Of course, I actually don't think that's Fenway, but anyhow, you need the whole spectrum from radio to gamma rays and everything in between in order to, I don't know where it's from. Anyhow, to really get a full picture of the universe. Oh, so it's Cleveland. Okay. Anyhow, not my photo. So what do astronomers do and why do they do it? So there's a little bit of misconception about what telescopes do. So let me start with what that involves. There are three goals of a telescope in very rough form, very basic forms. The first is to magnify. And this is what most people think of when they think of telescopes. They think that they kind of work like binoculars, that you go and you look out and you see something that's really, really tiny and it makes it bigger. And that's to some degree true. I mean, that's what a telescope can do. But that's not all it does. More importantly, it collects light. And that means that you can get more photons of very faint objects that are often very far away. That's very important because our eyes cannot do that, no matter how much we wish they could. And the third thing is, we'll get to more, is it expands what we can see beyond the range of our eyes, what our eyes cannot see. If the electromagnetic spectrum were a keyboard, a piano keyboard, the amount that we could see may be 2 or 3 keys around middle C. It's really a very small portion of all of the light that's out there. So what astronomers do is they build telescopes to expand that vision both for magnification, faintness, and also getting outside those few keys on the keyboard. For example, just to give a number here, this is this amount of collecting space we have in the human eye. It's about 1/4 of an inch across. You can only collect light through the pupil. It's not very big, very good for getting around the Earth and interacting, but not so good when you're talking about getting very distant objects and seeing what's going on. By comparison, this is the 8-meter telescope that is now in Gemini North. And we were just talking a second ago before people came in. There are plans in the works to make a 30-meter telescope. It wouldn't be probably a single piece of glass like this, but it would be 30 meters is really big. I mean, the biggest amateur telescope would be probably 2 feet across. This is 27 feet across. So you're talking about making a surface area that's much, much bigger, and it can collect way more light. And the other thing that telescopes can do that human eye can't is that the human eye takes an image about 30 times a second. Not a very long exposure time. For some of the most famous images that we've ever had, it's the Hubble Extreme Deep Field, I believe, is the equivalent of 50 days worth of exposing time. And granted, you're stitching those together, but you can add those because you can. That's how it works. So these are what some of the things that telescopes do that we cannot. Okay, so what does that all mean? And let me just show you a couple of examples before we get back to sort of how we make the images. And going back to the need for different telescopes. So this is the famous Supernova Remnant, Cassiopeia A, and this is a star that exploded about 400 years ago in the night sky. And this is an image from Hubble, and it's it's nice. You can see some of the filamentary structure, and this stuff that we're seeing here is glowing at about 10,000 degrees, which again, pretty hot, and that's nice. But in order to sort of really see it, if you add in X-ray light from Chandra, you see that it's much different picture. So the difference between, go back, and we can add these together, and these are actually two separate images, and we'll get to the combined image in a little bit. And what do we do in order to get to these images? The images that come down from telescopes like Chandra and Hubble and so on and so forth, they come to us, well, from space telescopes, they come to us as ones and zeros. For example, a telescope like Chandra, we take the ones and zeros and we know where each photon has landed on the CCD detector. And there's an event table, and you can basically print out, you can name the photons if they wanted, and sometimes they do. And they translate those event tables into black and white images. And that's where Photoshop comes in. So in Photoshop, what people who make images from astronomical data do is that they make layers, which I'm sure if you guys have used Photoshop, are familiar with. And these layers are then colored. And this is where I think a lot of the confusion arises, is that people think that the colors from astronomical images are somehow, either they're randomly assigned, or they're either a real color image or a false color image. And I'll get to the topic of false color too, because that's a very unfortunate term, the term of false color, because it somehow implies that things are being faked. And again, we're back to this issue of Photoshop, and it somehow gives the public, at least, the perception that scientists are making it up and taking out their box of crayons and just coloring things as they want, like, oh, this part will be blue and this part will be red, and that's actually really not how we do it. So we instead translate what is this into, as I said, these event tables that are then made into black and white images. Just so you understand how something like Chandra works, Chandra's in space, like Hubble, and something goes off in the universe, Chandra observes it, and then it relays its data every 8 hours or so down from the satellite through what's called the Deep Space Network. And then those data are then sent to our headquarters at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, and eventually given to the scientists who proposed that observation. So it arrives to the scientists, obviously electronically, and there's no image at that point. Scientists then take the data and then probably do something like this, which is useful for the scientific community. That's a real X-ray image on the side. But it really isn't very useful for communicating to the public what is being seen, what the context is, and so on and so forth. So we need to find a way to translate the raw black and white data into something that's meaningful. And color helps give it meaning. So I'm going to give you one example that I showed quickly before, and that's this image, which is the so-called Pillars of Creation. This particular version, I'll show you an updated version later, was taken in 1995 by Hubble, and is perhaps one of the most famous astronomical images ever taken. The steps you see are just a byproduct of the camera on Hubble that took it. And when it came out, I think it really captured the imagination of a lot of people. It looks, unworldly. It looks like it's black and white. But it was in color. It looks even better. And the colors come from, more or less, in this particular case, red, green, and blue layers that have been stacked together. And I'm going to not remember exactly which layer is which, but these are not, the colors are layers of specific elements that are being emitted. So I think one's oxygens, one's sulfur, and I can't remember the third one off the top of my head. And this leads me to sort of talk about sort of the different ways that you can take astronomical images. Some astronomical images are called broadband images, which basically means that a telescope looks at a chunk of the electromagnetic radiation, all of visible light, let's say. And then in that broadband emission, you can choose to cut it up in different ways. You can choose to cut up low, medium, and high. You can do this for X-rays. You can do it for radio waves. You can do it however you want. This used to be the standard of how people would do astronomical imaging. They would low, medium, high to correspond to how the eye works. And that's one way to do it. And it also mirrored how photography was developed and how astronomy developed with photography over the 20th century. As we move into the 20th and 21st century, we now have way more colors and options at our disposal. The red, green, and blue palette does work sometimes and sometimes creates very spectacular imagery. However, it's not something that astronomers adhere to. You don't have to stick with that color scheme. It does make sense on a physically to some degree that the low represents the lowest energy, green the medium, and blue the highest. But the point is that astronomers sometimes adhere to that and sometimes don't. And it's not random, but there is an aesthetic component that goes into the decision. And it really is to show both what is the scientific point of the image and also what is the most beautiful image and striking image you can take. Because if you are making images that are distracting and not appropriate or not attractive to people, then they're not going to consume the information you're hoping to get out of that image. So for example, here's another example of an image that is not red, green, and blue at all. This is an X-ray image. It's an X-ray image of a supernova remnant called G292 and some other stuff at the end, which I forget. And this image, the important part of this image was to show the elements that a scientist can see with this expanding debris field from this exploded star. So, as you guys probably know, supernovas seed the universe with important elements like oxygen and silicon and the calcium in your bones and the iron in your blood. And understanding exactly how they do this is very important to astronomers and also for us, since we were a byproduct of some long ago supernova. So this particular image was colored using the color scheme down at the bottom. Oxygen is in yellow and orange, neon's in red, magnesium green, silicon and sulfur in blue. And it really depends on the data set you have and showing what is important and working with the scientists who took the data to sort of tell the story visually of what they're trying to communicate, and then finding that balance between making it aesthetically pleasing and also scientifically accurate is something that we do. So you always basically have to look a little bit deeper at the images to really find out what's going on. But I'll pause here for a moment to say that one of the things that we really pride ourselves on is that everything is transparent as far as what we do. There is, again, this potential mistrust of scientists and whatnot that they're somehow, manipulating the data in sort of negative way, doing things that are not real, it's made up. We've all heard there are conspiracy theories out there for everything from the moon landings to whatever. We take it very, very seriously that, in me working for NASA, that we are very open and honest about what is done to every single piece of data, and that it's reproducible. And we actually have a lot of tools that we make available to the public that you can go take the data and do the same thing. And that we don't just randomly color certain features a certain color. These are the layers of data. That's, the layer of oxygen is what it is, and we don't cut it out if it's inconvenient, or we don't, So, it's very important that, whatever decision is made about everything from cropping to color to whatever, that those are disclosed, because otherwise you leave room for criticism and disbelief. And we know that scientists don't need any more disbelievers out there right now. We know that we're here to sort of promote science, not give someone a reason to attack it. So that's one of the things that we are in my day job, very adamant about. And one of the reasons why we did the book was that we want people to understand, if they're curious, what actually goes into making these images. So there's no no potential for, I don't know, distrust. Sometimes we use images that involve more than 3 colors, as we did in the last one. This one involves 7. This is an image from Hubble of the galaxy NGC 1512. And again, by adding all these separate pieces up, combining them in one image, that's what you see in the middle. But we also make the separate layers available too, so that you can, as a layperson or just interested, whatever, you can see what went into the final product. A lot of people won't go and find the final product, but we make that available in case they want to. So it's not a mystery, like, hey, you just made that up. Going on further to talk about different kinds of objects that give off different kinds of light, perhaps the nearest and dearest to us that we can all relate to is our sun. I mean, these are images, from the Solar Dynamic Observatory. And I can't remember exactly how many different wavelengths are represented here, but a handful. Our sun gives off almost every kind of light from radio waves to gamma rays, and we need to study all of them. And so these kinds of images are used to sort of help show people the different features of the sun, what happens in different wavelengths, what happens at different temperatures, and they're all important. And so I think, again, the most important thing to do with something like this is to explain to the public what we're doing, why the colors are used, or at least which ones are used. Because the thing is, color adds information. If we were to look at a weather map of, we're getting a big storm coming through here in Seattle, you look at a Doppler radar screen, if it's in black and white, you don't know where the heaviest rain is. You look at a Doppler radar screen with, red is the most intense and green's the least, you understand more, you get more information. It's the same thing in astronomy. It's the same thing in scientific images. It's just you have to explain it. You just can't just assume people without that knowledge base are going to automatically understand without that explanation and that, sort of jargon-free example. So, going elsewhere in the solar system, we take pictures of other planets too. So color is important. We call Mars the red planet for good reason. This is a picture taken from the Curiosity rover back in 2012. We have to calibrate. What the planetary guys do is that they will calibrate the sky so that it matches up with a sky that we would recognize, and to therefore calibrate the red. So you can land on Mars and take pictures, but if it's not calibrated right, it just looks odd. So this is a merged, I think, from the two images above to the one below. And so there are color corrections done all the time, especially in science, and again, for good reason. Sometimes we take images from different kinds of telescopes. I've so far, I think, just shown you images of different colors found within one wavelength, X-rays or visible light. Is there a reason to combine them together? One of the most famous objects is the Crab Nebula. It exploded, was it 10? I can't remember the date. About 1,000 years ago. What's that?
1054.
There you go. Thank you. Almost 1,000 years ago. So that famous object was observed by Chinese and other astronomers around the world at the time. And since then, it's probably one of the most observed objects, I would say, in astronomy. And this will show you what it looks like if you look at it in different kinds of light. This is the X-ray image from Chandra. You can see it sort of looks like a little vortex or whatever. This is some infrared data also. And if you add in Hubble optical, that's that. You can see the outer shell that it's moving into. And you combine them all together, and it really provides context that I think otherwise is just lost. And you need to have these pictures. But again, you notice the color scheme, blue, red, and purple. It doesn't really follow the chromatic, which is the red, green, blue color scheme. These decisions are made, again, by working with the scientists and working with the professionals about what's going to make the best image. And we, again, try to fully disclose sort of every step along the way so that when this image goes out there, it's not just thrown out there into the public. It actually has some context. And we now have, in the astronomical community, we've done a lot of work with metadata so that even if these things are randomly found on the internet, the some of the important information about color and other things are embedded within the data, so that we're trying to make it as uniform as possible, that there's sort of proof of purchase. If you find this image, you can trace it back to where it really came from, and that information is not lost. Similarly, we can look at things like galaxies. This is the Pinwheel Galaxy, otherwise known as M101. And this takes 4 different telescopes. X-rays from Chandra. It takes, I think that's Galex, which is ultraviolet. Then we have, that is Spitzer, and this is Hubble, I believe. Put them all together, and you end up with that. Again, some of these images are, again, look kind of funny to me when they don't have the different wavelengths stuck together. And each element gives you different pieces of information. X-rays will tell you where exploded stars are, where X-ray binaries are. Infrared, for example, will tell you where the dust is in a galaxy. The optical light will tell you where the older stars are, and ultraviolet will tell you where the younger stars are. So you put all these pieces together to get a complete picture. Another example is the Cats Eye Nebula, which is a planetary nebula, which actually has nothing to do with a planet, which is a really bad name for this category. It's really just the end life of a star like our sun. Our sun one day will go through this phase when it runs out of fuel and sheds its outer layers. And so we can look at it with X-rays, and you can see the middle of it. It's just sort of the hotter cocoon that's right around the star. And then you add in the optical layers, and then you can see sort of what has happened in the context of the shedded layers with the ongoing heated material in the middle. So just to shift gears a little bit, I just wanted to mention that, again, this is not all random. We don't do this without thought or without sort of understanding some of the consequences. We study some of these choices. My coworker, Kim Arcandis, led a group called Aesthetics and Astronomy. It's a research organization project that has combined astrophysicists with psychologists and studying how people react to color and how they react to color in scientific imagery, in particular astronomical imagery, but also to better really understand, as opposed to just going with our sort of gut feeling, like, I think this works for the public. There's really some research behind what is useful and what is not, what's confusing, what is not. And part of that has to do with understanding visual grammar. We understand that those mountains in the background are bluer, and that means they're farther away. So there are ways to sort of select color in astronomical imagery that will help guide the eye in a way that makes us as humans interpret the data in a way that will perhaps convey depth, convey distance, that this is behind that, this is closer than that. Also the issue of heat. We talk about, if you're familiar with physics, you know that the hottest things are blue. But if you talk to the public, they'll say that red is hot. So what do you do in that situation? If you're trying to convey something that's hot, do you make it blue, which is scientifically correct, or do you make it red? And these are choices that you have. I mean, you're not distorting anything. You're simply making a color choice. And so this was one example that we tested, or Kim's group tested. This is NGC 4696. It's an elliptical galaxy in the Centaurus cluster, about 150 million light years from Earth. And we originally did this, I think. This was the original one. And so blue is the hotter stuff. That's what you want it to be. But people, when you tested it, they thought that the redder stuff was hotter. So it's a matter of, you can flip them. And, it seems like an arbitrary choice, but it's actually important, because if your point is to tell people what's hot in an image and what is cool, you have to understand your audience. And by the way, the Aesthetics and Astronomy project includes astrophysicists that we test, and it's often diametrically opposed to what the public thinks. So it depends on what your audience is. If you're talking to your scientific colleagues, you give an image where blue is hot. But if you really want the public to sort of, at their first glance when they're flipping through their news, or they're looking at astronomy picture of the day, if you want them to understand or think about something being hot, you might pick red. And Is there a right way to do it? Not really. You can argue both ways. But I think the most important thing is that you give it thought and you disclose what you've done, and label what colors are what. Be very upfront about it. And I think the other thing that our research has shown is that the public will voraciously consume any of this stuff, but you really have to have clear information that goes with it, because otherwise it's meaningless at the end. So I mean, we found that almost what the image looked like didn't matter. It did matter, of course, but it was also equally important to have well-written, clear captions to go with it. Otherwise, you could have the most beautiful image in the world, and people might look at it and be like, "Hey, that's cool," and walk on. Or you can have something that's kind of funky looking, and you explain it well enough, and you're going to hook them. And my job is, I think, to hook people on science and to get them, engaged. And so I think that images are one of the strongest things we have going for us in science, especially in a field like astronomy. Keep going. So I just wanted to just shift gears a little bit and talk about something that was kind of a fun topic at the end of the Coloring the Universe book that is our final chapter, because it's one of these things that always makes the rounds of the internet or whatever, one way or another, and often involves astronomy. It's the phenomenon of, I spelled it wrong, pareidolia. There's an extra D in there, so ignore that first D. And this is the phenomenon of seeing familiar things, especially faces, in noise or data or whatever. And you always hear about seeing Jesus Christ in toast, or the Virgin Mary on a windowsill, whatever. But it happens all the time in astronomy, which we thought was kind of a funny thing. And so we kind of played with it a little bit at the end of the book. And one of the most famous cases is the face on Mars. That's the corner image is the image from Viking in 1976, and it looks kind of like a face, and it freaked people out totally. I mean, this is pre-internet, obviously, so imagine what would happen now. So this is an updated version from the Mars Reconnaissance Orbiter back in 2012. There is no face, there is no person. I think there were some bad movies actually made on the lower, because of the lower right image. I blame Hollywood. But it's not just Mars. This image that I was involved with, we put out, and it was nicknamed the Hand of God, which it was not our name for it at all. We knew it had sort of hand-like structures, but you can imagine that people saw this in, I don't know, apocalypse or whatever was coming. But there's a ton of these images in astronomy, and they're we kind of, I think you just kind of play with it and just kind of go with it. But it's also another way when it happens to sort of give people a reason to hook them in and explain what's really going on. That this is really a pulsar in the middle of that thing that's spewing out high energy X-rays, and that this is what it is. It's actually not, someone reaching and anyhow. But there's things that are all over the place. This is the famous Horsehead Nebula. That why? Because it looks like a horse head. This is not. Some of this is pretty obvious. Some of it's pretty far-fetched. But if you're interested, you could take a look at the last chapter. I did want to just sort of end by just mentioning the book one more time. This is that one. It's in the BBC Sky at Night. We just got a review, which was fun. And just mention a couple of other, if you want to learn more about any of this stuff, I'm going to be giving a town hall event on Tuesday about the light book. So it'll be not so much about astronomy as much as it is about the whole electromagnetic spectrum, which I need to say better when I say it that many times. And Travis Rector, who was the first author of the Coloring the Universe book, is going to be in town 2 times in the next couple weeks, one at Ada's, which is in Capitol Hill, and then he's also giving a talk to the Seattle Astronomical Society meeting over on UW's campus, and I think and both of those are open to the public and free. So I would encourage you, if you guys are interested in learning more of the real nuts and bolts about at least visible light imagery and all that, to try to get to one of those talks with Travis, or if you want to hear more about the light book, I encourage you to come to that one. And I will just end by saying this is how you can get in touch with me. I do have the day job, which is the Harvard address, and then I have a Gmail account for my stuff on the side, which is basically the books. So with that, I want to thank you, and I'm happy to take any questions. Thanks. Oh.
that are watching online, they can submit questions.
Oh, okay. All right, there's a question here.
Hi, thank you very much. That's a great talk.
Thank you.
You mentioned the importance of communicating the choices of colour that were made in creating a given image, but there often seems to be an inconsistent way of doing it. Sometimes it's in text, sometimes there's a colour key. Have you explored having a standard way of including a colour key on the image so that it travels with the image? Because obviously a lot of the formats of the images that get transferred around the internet don't have an easy way of taking that metadata with it. So actually including a colour key on the image itself could be a useful way, and if it's standardized, could be a useful way of helping the public understand those choices.
Yeah, I mean that would be ideal. I would have to say that it's sort of like herding cats with astronomers. Everyone does their own thing to some degree, and there has been a lot of even just getting the metadata stuff worked out and having the major observatories participate. And Curtis can talk more about this. I met Curtis years ago with worldwide telescope stuff, and part of that is getting the images in a format that is uniform enough that it can be used in something like worldwide telescope, and having a consistent, to have a color key on something that goes out. You're going to have the people who don't want any labels on their images. You're going to have people. There's so many different, and you have people. You have major observatories that have staffs like ours that will make images and will work together with other major observatories. You also have people, or sort of single astronomers, who make a pretty picture and put it out there. So it's really hard to get that consistency. I think it would be great, to sort of have that sort of template almost. It's really hard to get there, though. So unfortunately, I think. So I think the best you can do is, one of the things we've done, for example, on the Chandra website, is that if we do a multi-wavelength image, we always have a clickable, layer. So you can say, oh, this is the radio, and you can play with them and stack them and whatever. So you can see what's what. Because if you see one of these combined images, it's really hard to piece out what is what and what information comes from what layer. So, we try to do it to what we think is the best standard, but it's hard to get everyone else on the same page, I guess. It's probably, unfortunately, my sort of non-answer for that. Good idea. Yeah. Yes.
Is there sort of an ordering to the layering that you do, or do you always make them opaque so you can see through things, or is that important?
There's not an ordering per se, and sometimes, for example, we will make some layers a little less opaque, for example. So if we're trying to show, for example, some of these X-ray images, and we want to put it on a starry background because that makes it look less abstract, psychedelic, funky jellyfish floating in the air kind of thing, then we make and if that star field's really intense, it might overpower the X-rays, so we might tone down the layer. So there are choices like that. Sometimes they're all equal. It really depends, but we try to, usually they're pretty much as they are, especially if it's like radio and X-ray, or but there are some times when you might, tone down the star field, for example, or bring up something else a little more. The layers are great for that. So, yeah.
I noticed on the layered images that you had of the nebula, the spectrums had slightly different frequencies. Is that because different scientific teams have access to different equipment that actually expose at different frequencies? Is that why?
Well, so every observation so if you request, for Chandra, for example, you are going to use a certain instrument and you're going to get a certain amount of information back from over a certain wavelength range. And then when you get that information back, some of that information from various wavelengths is not as useful as others. It's either, for example, it gives off very strong emission at a certain wavelength. So you would actually splice out just that wavelength for that purpose. So it's not that it's different scientists, it's that you're just really using the pieces of data that make the most sense. Also, with something like Hubble or a ground-based telescope, you can choose to use different filters. You actually physically put different filters on the telescope, so you're only letting certain light come through. So it really depends on where the data came from, what it was used for originally. All these data go into public archives at a certain point, so for some of the images, you can just pull the best of what looks the best. It depends on when the image was made, and again, there's a lot of variables that go into it. So I don't know if that answers your question or not.
Yeah, and I guess the follow-on to that, where I was kind of going, was if I look at those images and realize that they're slightly different frequencies, it seems like that'd be difficult to compare and contrast in an apple-to-apple fashion, right? But it makes you make it sound like that the scientists actually have much more layering of frequencies available to them so that they can go pull together the exact slice of the spectrum that they're interested in comparing, horsehead to cat's eye to crab and all that stuff, right?
Yeah. And there's certain wavelengths or frequencies that are like crucial. Iron is emitted a certain line, or certain very key frequencies that you are sort of diagnostic tools that you can use throughout astronomy or whatever. So it really it definitely depends on the image, and it depends on the science being done, and then. Making the spectacular image is generally not the first order of business. It's to get the science done. So what we do is that we use whatever data we can get our hands on, because the way that all these telescopes work is that you propose to a committee, usually once a year, I want to look at this galaxy for this long using this instrument, give me time and money to do that. And if they get it, great, and then they're off to write their paper. And that they have that data more or less for about a year, and then it becomes public access data, and so-called in the open archives. So it depends on when we do the image. Sometimes we have only access to that data. Sometimes we can pull stuff from the archive to enhance the data. But the scientists themselves know exactly what, the way they can compare one to another and how it all fits together. It's just sometimes we don't have the full range to do that. If that makes sense. So, yes.
Do you ever confer with counterparts in, say, microbiology or other sort of scale fields who have similar sort of the eye can't perceive the level of detail that they're observing? And obviously, they have different specific intents because they're really worried about iron emission lines per se. But in terms of just communicating science literacy to the public, some of the same sort of scholar questions.
Yeah, and actually, that's some of the. Not to just hawk my book, but some of the things we have in the white book, we talk about that because you definitely have some of the same issues. You're trying to see the unseen or unseeable, and you're trying to explain that. One example I can share is that Alyssa Goodman, who's a colleague of Curtis, she started this whole initiative with using medical imaging with astronomical imaging and merging those two together because they're using these techniques to get MRIs of the brain and get 3D, all this stuff. And she helped implement that for astronomical images. And we used that actually for Cassiopeia A. We did a 3D model. So there are definitely ways that we can borrow from other fields and learn from other fields. And I think that is something that we can do more of as far as merging, using sort of best practices for how do you explain these very difficult concepts to across different sciences. An ideal world would be that there was some uniformity, right? So that it's not confusing to the non-expert that, oh, well, this time they did this way and I don't get this. But I think that's a goal. It's not really, but we're working on it. Let's put it that way. Yeah.
So you're basically serving a projection from the wide range that you have of information into something visible.
Yes.
Is there any format nowadays in digital world that you could just, have the full spectrum sent and you have shaders that generates specific views that you want?
Well, kind of worldwide. I mean, are you saying you want just pick an object and then see it in all the different kinds of light? Or
For example of the red and blue.
Yes.
You could have this view or that view. Mm-hmm. And nowadays, when you had books, then you could serve only one.
Mm-hmm.
But in digital format, you could have different, this shows the materials, this shows the heat, this shows, and have different views.
Yeah, I mean, first of all, I have to say, I mentioned earlier, there's almost all of the major telescopes now have publicly available tools that you can download and grab real data, and you can make your own image and do it yourself. That's a little more work than maybe what you're suggesting. As far as seeing it and just being able to flip the colors, with a switch or a button, we're not quite there yet. There are tools like, for example, in, say, Worldwide Telescope, where you can go to an object and see every image that's been taken of it in, probably not every wavelength, but, most of the wavelengths that are available. And you can click through them and see, and again, get some explanation for what the colors are. I'm not sure we're ready yet to just be like, show me what the heat is and show me what this is quite yet, but that would be a really fun tool to have. And it would be very informative, right? So you could really just sort of say, I want to know what, this is doing. So you talk to Jonathan Fay about when he comes back. Tell him you want that tool in Worldwide Telescope in all his spare time. Yeah. Yes.
Perhaps related to what you were just saying, this is definitely getting more technical, but has there been any effort into perhaps creating a new file format that all it does is for astronomy images, or I guess even for medical images, layers this information and says, okay, this layer contains H alpha data, this layer contains oxygen data, but the image format, the file format itself has that embedded in it, so it's not a JPEG or RAW or anything. And that would allow you to easily click through and recolor all of these layers, like instantly.
I have no idea. That is not my experience. It's a great question. That's sort of a Robert Hurt question. There are people who I know could answer that question, but I'm not sure about that. It would be, something to consider, for sure. Anything else?
Any other questions? Well, with that, let's give her a...
Thanks for having me.